If not, it would not be able to plot them on the maps the way you see it.
Okay, the program is translating.
So we move on to this really excruciatingly painful but very, 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 very important concept called coordinates and projection. So I'm hoping to get this out of the way before we go for the break, for which I think we have about 15 minutes. 10 minutes? Okay. So, well, I'm going to do a lot of hand waving, which I'm fine with. So, so coordinates and projections. Basic stuff. What are coordinates? So to understand coordinates, you have to first understand the shape of the Earth. So the correct answer to what is the shape of the Earth is actually an ellipsoid. So an ellipsoid is the shape of the Earth. It is pretty hard to manage, but that is what it is. What is an ellipsoid? It is a three-dimensional closed geometric shape, all planar sections of which are ellipses and circles. Sorry. Okay. So dealing with ellipsoids are hard. So what do? In GIS, we basically use a spheroid. What is a spheroid? It is basically a three-dimensional shape which is obtained by rotating the ellipse on its major and minor axis. But again, spheroids are not easy to work with. So what do you actually use, or at least what ArcGIS uses, is a sphere, right? Which is, when do they use spheres? They only use spheres to do mathematical calculations. And how do they use? They don't use just any sphere. They use a sphere which basically performs math, which is constructed such that the surface area of the sphere is the same as that of the spheroid. And there's a name for that. It's called an othalic sphere. But when you talk about coordinates, right, in this othalic sphere, you basically have to look at latitudes and longitudes. This is fairly basic information most of you know. But just to run through very quickly, you may have already heard of them, like called parallels and medians. How are these stored? These are basically stored based on 360 degrees, such that each degree is 60 minutes and each minute is 60 seconds. So what is a latitude? It basically helps you find features between the north and the south pole. Where is the zero? The zero is at the equator. So everything above the equator will be 0 through 90 north. Everything below the equator will be 0 to 90 south. Similarly, longitudes will help you look at stuff from east to west. Where is the zero? The zero is at the prime meridian, which I had forgotten is actually in Greenwich in Great Britain. And everything to the east of the prime meridian from 0 to 180 degrees east will be in the eastern hemisphere. Everything to the west will be 0 to 180 west, right? So latitudes, longitudes are probably the most common ways to look at coordinates. But there is this other thing which keeps coming up, which I have spent a lot of time getting around my head, and hopefully this will make it simple for you. This is called decimal degrees. I never understood this. This is one of the colonial leftovers from where I come from. So this is basically another way to denote coordinates. A simple way to understand how to go by through latitudes, longitudes, and degree decimals. Look at the latitude for Broadway and 42nd Street in New York City. That is the number of degrees, so 40 degrees, 45 minutes, and 21 seconds. How do you convert this to degrees decimals? You take 45 minutes, which is the second term right here, divide that by 60, you will get 0.75 degrees. Take 21 seconds, divide that by 3600, and you will get so many degrees for the seconds. And then you basically add everything up, and that is your degree decimal for the latitude. And you will do the same for the longitude. And here is a shameless plug that Microsoft, those of you who are Mac users, I'm sorry, but for those of you who prefer using Windows, there is the calculator that comes built in, has a feature that will let you do this on the fly. And it has been incredibly useful in my own work, so hopefully you'll find it useful. So there you go. One thing to remember about decimal degrees when you use it is that any coordinate which is in the southern or western hemispheres, have negative values. This took me about 30 minutes to decipher when I first saw this, and I could not for the life of me figure why there's a negative sign. But oh, there you go. So this is something which is really painful, but if you see a negative sign, it just means hemisphere. So after coordinates, which we have finished in like 6 minutes, so we have like 4 or 5 minutes for projections. So projections are basically the way of converting points on a globe to a flat map, right? So the Earth's surface is not flat, but the map that you actually generate and do analysis is flat. So you need a way to project information which is on a round reference globe onto a flat map. One problem with this is that there is always distortion. No matter what you do, there is distortion. What do I mean by distortion? There are 4 types of distortions. One distortion is in shape. That means the shape of the object as it exists on a globe may not be the same shape that it exists on a map. Similarly, the areas may not be the same. Similarly, the direction may not be the same. What do I mean by direction? All I mean is the angle of this object from the North Pole, right? So you want even that angle to be the same. And in some projections, the angle may get distorted. And lastly, you want measures of distance to be the same. So if you want the distance between DC and New York City to be so many miles, you want the same thing to also exist on your map. So this distortion is something that cannot be avoided. So this is the big question that you will always ask yourself with a map. Which projection do I use? And the answer is another question. Which spatial property do you want to keep? So there is obviously a trade-off that is involved depending on what you want to do with your maps, right? Depending on whether you want to keep shape, area, direction, or distance, you will choose different types of projections. An easy way to get around this is to use examples. Look at the Mercator projection, for instance. The Mercator projection preserves shape. But what it will mess up, so this is a really small picture, I apologize. So the stuff in white right above is Greenland. And the stuff right here is Africa. And this is the standard example that's provided with Mercator to say there's no way Greenland is that big compared to Africa. But you see, this is the problem. It preserves the shape of as in basically the borders of the different objects, but it does not preserve size, right? So if you are going to calculate area of any polygon in your map, if you use Mercator projection to do that, you're going to get errors, mistakes, so on and so forth. Another example, if you use a sinusoidal projection, this preserves area, but does not preserve the other 3. Then you have equal area cylindrical. It preserves area, but the shapes are distorted. And this is another one, which is the azimuthal equidistant, which preserves distance. So if you are involved in stuff to calculate distance, and for all of us who do regression discontinuity stuff, you calculate distance to border, distance to so and so, you need to be in a position to use a projection that preserves distance. And if you do not use the appropriate projection, your distances all get distorted. And lastly, you have Robinson, which is middle ground. By middle ground, I basically mean in the middle of nowhere. It does not preserve any of the 4, but it does a decent job on all 4, right? And these are the common things that you will come across as you deal with stuff. Some more stuff on projections, which I will not go through in detail. There are different types of projections. One are called planar projections, which are useful for polar maps. The cylindrical projections, which are good for equatorial maps. So if the area that you wish to study lies in and around the equator, you would use a cylindrical projection, or a conic, depending on how far away from the poles you are. Another thing to keep in mind is the light source. Light source basically talks about how you view the object. From where does say GIS view the object? So you have different types depending on whether you view the object from the center of the Earth, whether you view the object from one pole to another, as in that is your line of sight and how you view the object, or whether you view the object from space. And there is one more thing called aspect, which is called how the globe is oriented to your projection surface. As you can imagine, this thing gets complicated really, really quickly. And thankfully, because we have to go for a break very quickly, I'm going to hand wave and say, if you ever use projections, please make sure you take into account all of these. But I'll make life simple for you. How to make life simple is to point out some simple things that people generally use when it comes to projections. So when you look at the World Geodetic System, which is also called the WGS 84, this is the most common geographic coordinate system that is being used, right? A lot of maps that you will find online or through various sources will use this particular coordinate system. This is the same coordinate system that is used by the GPS in your car. And how does this work? The starting point for this coordinate system is this Earth center, and which basically makes it really convenient or correct for no matter which part of the world you wish to study. So essentially, if you draw a world map, for instance, using this projection or coordinate system is appropriate for you. Why? Because it does not favor some parts of the globe over other parts of the globe, right? Yeah. Another one, which is the UTM. And the UTM, for those of you who study microdata, this is what you would need. UTM basically is a projected coordinated system which basically divides the world into various zones. So you basically look at the world between 80 degrees south and 84 degrees north, and this area is divided into 60 zones, which each zone having a width of 6 degrees in longitude. So zone 1 basically covers 180 degrees to 174 degrees west. And the numbering increases as we go to the east, and finally zone 60 ends at the other end. This is very, very useful for real fine scale mapping, because what it does is for each zone right here, it gives you the correct projection for that zone. So there was a time when I was working on Ghana for some reason, and Ghana was right here, and if you wanted to actually look at compute distances, areas, or do whatever GIS analysis you want, and you want to focus on Ghana, you would use the UTM for that zone, for where Ghana is located. That will give you the most accurate distance. And pop. Okay.
Quarter after or we convene?
I don't know, whenever we want to come in.
My watch, which is 18 after by that clock.
Okay. No. Yeah, I've done it, I think, maybe once, twice before, but I have to